Okay, let's look at a roller coaster that starts at the top of a hill, like right here. It'll start from rest, and we will solve this using the conservation of energy. Okay, so here's our roller coaster. And let's look at the first hill. We'll say it's 30 meters high. Then we'll look at the second hill, call it 15 meters high. And let's look at starting right here. So our roller coaster has already made it up the hill, and it's going to start right here. We'll call this point A, and it's going to start with an initial velocity of 0. So starts from rest at the top of the hill. Alright, we'll also look down at the bottom of this first hill, which we'll call point B. And obviously the roller coaster is moving right there, so we'll call that velocity at point B. And then our third and final point we'll look at will be at the top of the second hill, which we'll call point C. And again, the roller coaster will be moving there with a velocity, which we'll call velocity at point C. Okay, so what we want to solve for in this problem are these two right here. So we want to calculate the velocity at the bottom of the first hill, okay, so point B, and the top of the second hill, which would be point C. Now we're going to do this using conservation of energy, so it's also important that we go ahead and say that we're going to neglect friction, so we won't be losing any energy to heat or anything. Alright, let's start by looking at point A right up here. And if we look at point A, we always need to ask ourselves two questions, because we want to look at how much energy is there. What types of energy do you have at point A? So you ask yourself the two questions. You say, do I have height? And if you have height, then you're going to have potential energy, and you would have that potential energy at point A. And then ask yourself if you have velocity, because if you have velocity, then you're going to have kinetic energy at point A. So we know that we are on this hill, so we have height, but it starts from rest, so you have no velocity. So no velocity means no kinetic energy, but because you have height, you do have this potential energy at A. Alright, we'll go look at point B and ask ourselves the same two questions. Do you have height? Because if we do, we would have the potential energy at point B. And do you have velocity? Because if we do, we would have the kinetic energy at point B. So, no height here. You're on the ground. So no height is no potential energy at point B. But you are moving. You do have velocity, so therefore, yes, we have kinetic energy at B. And finally, we'll look at point C. Again, same two questions. Do you have height? Because that would mean we have potential energy at C. And do we have velocity? Because that would mean we'd have kinetic energy at C. So yes, you've got height. You're 15 meters above the ground. And yes, you've got velocity. You are moving at point C. So you've got both of these. So now we want to go and look at our total energy at each point. Okay? So we know at A, my total energy, if I add up all my energies, you've only got the potential energy, so my total energy is the potential energy at A. I can't add kinetic energy there because you don't have any. Do the same thing at B. Look at all your total energies at B. So my total energy at B, or the sum of the energies at B, remember this Greek letter sigma means the sum, S-U-M, to add them up. So I would add up these energies. I'd add this, which is 0, to this, which is kinetic energy at B. So all you have is the kinetic energy at B. And finally, same thing at C. Add up all the energies at C, and now you've got both. So now you're going to add potential energy at C to the kinetic energy at C. Okay, so now that we've looked at this basic breakdown of what types of energy we have at our 3 points, we can go ahead and use the conservation of energy, and we can use that to calculate the velocity at the bottom of the first hill and at the top of the second hill. And we do that because conservation of energy tells me that the total energy at point A is equal to the total energy at point B and equal to the total energy at point C. And that's the same for everywhere in between. It's also the same amount of total energy here, 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 everywhere, because it cannot be created or destroyed. So my total energy at A, right here, like I just said, is equal to the total energy at B, which is equal to the total energy at C. Okay, that's your basic idea of the conservation of energy. So that gives me like several different equations. I'm going to start by looking at the total energy at A equals total energy at B. That means these two things right here equal to each other. So I can write that out. Total energy at A equals the total energy at B. And now I'm going to plug in. My total energy at A is the potential energy at A. And my total energy at B is the kinetic energy at B. So fill that in. All right. And now we know that the formulas for potential energy is mgh, and the formula for kinetic energy is 1/2 mv squared. So I can replace these things with that. The mass times the gravity times the height at A, okay? And I have to distinguish this. It's height at A. There's different heights everywhere on this roller coaster track, so it's really, really, really important that we distinguish that out. However, the gravity is the same everywhere. It's Earth everywhere, so I don't need to say gravity at A. And it's the same roller coaster everywhere, so I don't need to say mass at A. But the height does change. You do have to make that distinction. Okay, and then equals, and now we plug in for kinetic energy, 1/2 mass times velocity. Remember, it is squared. And again, it's the velocity at B. Velocity changes all along this roller coaster, so it is super important that you distinguish that, just like we did with the height at A. All right, now, we know some numbers in here, but first I want to go ahead and solve this out for the velocity at B, and then I'll plug those things in. So if I'm going to solve for the velocity at B, remember, the mass is the same everywhere, and because both of these have one mass in each quantity, I can cancel them out. All right, so now we would have the gravity times the height at A is equal to 1/2 the velocity at B squared, because we took out the masses. So I'm going to get rid of this 1/2 by multiplying both sides by 2. When I do that, 2 cancels with the half. Of course, you have to do that to the other side. So that'll leave you with your 2GHA on this side is equal to what's left over here, which is VB squared. One step left to solve. It's VB squared. To undo that, you have to take the square root. Of course, you do that to both sides. And now you've got the velocity at B equals the square root of 2 times the gravity times the height at A. We can plug in our numbers. We know gravity is 9.8 meters per second squared, and the height at A is 30 meters. So 2 times 9.8 meters per second squared times the 30 meters at A, square root of all of that, and you get 24.2 meters per second. Okay, so that is how fast the roller coaster is going right here. All right, now, a little bit of common sense will tell you that it's not going as fast right here. Okay, it's moving, so obviously it's going faster than 0, but it's not going as fast as 24.2 meters per second because, you know, it's made up to the top of the hill, it's slowed down some, but it is still moving. Okay, so to do this, I'm going to go ahead. I know that my total energy at A is equal to the total energy at C, so we can write this out. Total energy at A equals total energy at C, and now we'll do the same thing we did up here. I'm going to plug that stuff in. My total energy at A is the potential energy at A, and the total energy at C is the potential energy at C plus the kinetic energy at C. Okay, so here's my potential energy at C plus the kinetic energy at C. Okay? All right, again, your masses will cancel. And so to solve it, the next thing I'm going to do is I'm going to subtract the G times HC from this side. Okay, so I'm going to subtract that, and that'll leave me with 1/2 VC squared over here. So if I subtract gravity times the height at C from this side, you have to do it to that side. And that'll leave you with your gravity times the height at A minus gravity times the height at C. And it's equal to what you have left over here. We just got rid of all this, so it's equal to 1/2 the velocity at C squared. And then because I want to solve for VC, I'm going to go ahead and first get rid of the 1/2. So I'll do that just like we did up here by multiplying by 2. 2 times a half cancels that out. And of course you have to do it to both sides. All right, so now I'm going to solve this out, and if you like distribute this in, you have to be careful. So it's 2 times G times HA and then minus, but this isn't quite right. Like I said, you have to distribute this in. It's also 2 times the gravity times the height at C, so don't forget to do that. That is an easy way to make a mistake. All right, and then it's equal to what's left over here, which is just your VC squared. All right, also notice that both of these quantities on this side have a 2 times gravity in common. So I can actually factor that out. You don't have to, it just makes things a little easier later on, but not necessary. All right, so if I factor that out, then you have left the HA from right here, and then minus the HC from over there. And of course, that's equal to VC squared. Just like above, we have one step left. I have to take the square root, do this to both sides, and you're left with the velocity at c is equal to 2 times the gravity. Make sure this is all in parentheses because it's this 2g is times HA and times the minus HC. Okay, so put that in there. And then plug in our numbers. Again, you know gravity is 9.8 meters per second squared. The height at A is your 30 meters. And the height at C is your 15 meters. So when you put all this in the calculator, you get 17.1 meters per second. And like we said before, it should be smaller than here. It should be slower than 24.2. But it's not obviously less than 0 because it is moving there. So it makes perfect sense that these would be your answers, which is always a good way to check to make sure you've done it right. Look to see if they're reasonable and if they make sense. If you've gotten something like outrageous, like hundreds of meters per second, well, that's pretty fast. I don't think that's reasonable. All right.